Well, hello, my Bio 111 class. All righty, we are going to pick up on bonding. So let's go ahead and share my PowerPoint with you. If you're going in the order of your PowerPoint, you will see that I skipped over covalent bonding. We will go back to covalent bonding. We're going to start ourselves with ionic bonding. So ionic bonding is when your atoms will strip electrons from their bonding partners. What does that mean? That means one atom will take electrons and the other one gives it. And so when one takes it, that leaves them with a negative charge. When the other one gives it, that's going to leave them with a positive charge because they gave away an electron. And so when you have a charged atom or molecule, that charged is going to be called an ion. So here is a perfect example. So what we're looking at is we're looking at sodium and chloride. Sodium, if you recall, looking at your periodic table, sodium is going to have 11 protons in its nucleus. And your chloride is going to have 17 protons in its nucleus. So let's go ahead and draw that out. 11 protons in the nucleus, okay? So let's start with the sodium. If it has 11 protons in the nucleus, before there are any type of reactions taking place, it's going to have 11 electrons. Let's double check and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, perfect. 11 electrons. And so the positive and negatives are going to make this a perfectly neutral atom. Your chlorine, if you look on your periodic table, it's number 17. That means it has 17 protons in the nucleus. If it has 17 protons before any reactions take place, there's going to be 17 electrons. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So as you can see, yes, it does have 17 electrons orbiting, oops, there's a little sloppy 7, orbiting the nucleus. So that is going to give it a perfect neutral charge. Excuse me. But what you know from the octet rule is even though these are neutral atoms, they're not happy. They're not happy in the fact that their outer valence shell wants to have 8 electrons in it in order to be considered non-reactive. So as you can see here, there is only 1 electron in that outer valence shell. So is it easier to give away 1 electron, or is it easier to take 7 electrons? Think about that. And then, so your chlorine is going to have 7 electrons in the valence. As you can see here, it's missing an electron. It's not missing one, it just wants 1 more in order to keep it from being reactive. So think about this. Is it easier for chlorine to give away 7 electrons, or is it easier for chlorine to just take 1 electron? I think you know the answer to this. So let's go check it out. Moving on. Okay, that doesn't quite line up, but I'm gonna go ahead and keep it as is. As you can see, your let's go ahead and do this. As you can see, your sodium gave away 1 of its electrons to chlorine. Chlorine accepted that electron. I'm going to tell you why you're going to end up with a charge on these atoms. If you recall, your sodium has 11 protons in the nucleus, and it had 11 electrons, but then it gave 1 away. So let's see how many it has left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It now has 10 electrons left because it gave 1 away. So that is going to give it a 1+ difference in charge. And then when you look at your chlorine has 17 protons in the nucleus. It had 17 electrons, but now it has 1 extra electron. So I'm not going to count them up. I'll just show you. See, there's that 1 extra electron. It got it from that sodium. So now it has 18 electrons. So that's going to give it a 1- charge. And so that one plus charge and that one minus charge, they're going to facilitate an attraction together. And that attraction is called the ionic bond. So the atom that has a positively charged ion, and that happened to have been the sodium, that is called the cation. The one that has a negatively charged ion, that was the chloride, the chlorine, that is an anion. So together they are attracted to each other to make that ionic bond. So whenever you have compounds that are formed by ionic bonds, those compounds are called ionic compounds or salts. The most popular salt we know of is sodium chloride, which is table salt, see, NaCl. So NaCl is actually Na plus and Cl minus, but that is understood. So we don't do that. We just put NaCl. They are found in nature as crystals. So as you can see here, you have an alternation between the anions and the cations, sodium chloride, sodium chloride, sodium chloride, and so forth. So most of the strongest bonds in organisms are going to be your covalent bonds. So let's go ahead and back up to the covalent bonds. So I'm going to back it up. It was first in the PowerPoints. I like to teach it second. So here are your covalent bonds. Covalent bonds are going to be when two atoms share electrons. And if you recall from previous lectures, I told you that there are some very specific atoms that are going to participate in covalent bonding. And they are going to be the ones that are called or considered organic atoms or organic elements, meaning you find them most, and they're going to be covalent bonding in living organisms. And that is CHNOPS, CHNOPS, carbon, hydrogen, nitrogen, oxygen, and sulfur. Those are your CHNOPS. So these guys, whenever you see these, you can mostly assume that they are covalent bonders, okay? I'll let you know, he likes to cheat. He's mostly a covalent bonder, but sometimes when he's used in inorganic element or inorganic molecules, he will ionically bond. Same thing, oops, I skipped one, sorry, phosphorus. Your phosphorus, same thing. You will see him making ions, and your oxygen too. But for the most part, the rule, these guys are going to be covalent bonders. So what does that mean to go covalently bond? So as you're looking here, we are looking at two hydrogen atoms, okay? Two hydrogen atoms, and you can see it's got the positive proton in the nucleus. You are seeing the electron cloud. So if you look at your periodic table, you will see hydrogen has proton number of 1, and that means he has an electron number of 1. So each of these are two different hydrogen atoms. So they're going to have an attraction together because there's an empty space, in quotes, within their shell. And that means that there is an orbital space. So this right here would be a space in that first shell, and this one here, because the first shell wants to be full at 2 electrons, but they each only have 1 electron. So what'll happen is there will be this attraction to each other's empty orbitals, okay? And then when that happens, their electron cloud is basically going to mesh over each other, and there will be this bond called the covalent bond. So neither one of them is giving up an electron, Neither one of us taking an electron, but they are sharing an electron. And that right there is the covalent bond. So what a molecule is, a molecule consists of two or more atoms held together by covalent bonds. And so a single covalent bond, or even a double covalent bond, we have single covalent bonds, we have double covalent bonds, we even have triple covalent bonds. So let's go ahead and look at, I showed you your hydrogen, how your hydrogen has that single covalent bond. Now, I could write it like this and take out that electron cloud and show you that, okay? That's showing you Lewis dot. Usually, we'll just go ahead and skip the dots and go straight for that, okay? See a double covalent bond, you're going to see in oxygen. So here's your oxygen. I'm going to show you the Lewis dot. Lewis dot structure is when you only show the valence electrons. So there is one here, boom, 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 and boom. You're going to find in oxygen, there are 6 valence electrons, and this oxygen has 6 valence electrons. Feel free to look back at your electron configuration diagram that are several slides back. That's the one that shows all of the shells, the circle shells, the first, the second, and the third shell. This is just showing the outer valence electrons, the ones sitting in the outer shell. So as you can see here, it wants to be full at 8 valence electrons, but there's only 6. 1, 2, 3, 4, 5, 6. And on the other one, there's only 6 too. So these will share, and this will share also. So what we do is we just draw it like this, boom and boom. There's an oxygen molecule. This is the hydrogen molecule. So that is a double covalent bond when you have 2 pair of electrons sharing within the molecule, 2 pair. Alrighty, so 2 pairs, 4 electrons total. Nitrogen has 5 valence electrons. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so you will get a share here, a share here, and a share here. So when you do that, let's go ahead and I'm going to do some highlighting for you. What's happening when you share that many, you are going to, this nitrogen here is essentially going to get to make time with these valence electrons, where you have 1, 2, 3, 4, 5, 6, 7, 8, and it completes the valence. But then this nitrogen here gets to make time with these valence electrons, where you get to have 1, 2, 3, 4, 5, 6, 7, 8. So that is how their valence shells get to be complete and happy. So since we like to go ahead and simplify it, when we draw the bonds, we just go like this. And that is nitrogen gas. Okay. All right, so I'm going to go ahead and leave this up. So you can see here, that they did do that Lewis dot structure, just like I was showing you in this example. That is just showing you the valence electrons, those in the outermost shell. And you can see that your hydrogen gas has a single bond, okay? Your oxygen gas has that double bond. So that is the exact example that I had shown you. We're going to back this up. Okay. So I'm going to keep these up here because there's something that you need to start to be able to see. Your hydrogen is going to make 1 bond. Oxygen, as you can see, because it needs to fill its valence, is always going to make 2 bonds. Sometimes it's a double bond with another with another atom, either oxygen or carbon, sometimes it's not. And then your nitrogen is always going to make 3 bonds. So one we have not done is carbon. Carbon is always going to make 4 bonds. When you look at your periodic table, you will see that your carbon is in the 4th column. Since it is in the 4th column, that tells you how many valence electrons it has. So let's go ahead and draw carbon out. If it's got 1, 2, 3, 4 valence electrons, that means that there's an empty space here, an empty space here, an empty space here, and an empty space here, because your carbon wants 8 valence electrons. Well, we need to fill each of those empty orbitals, we need to fill it with an electron in order for that carbon to be happy. So we need to bond something here, we need to bond something here, and here, and here. And that is what is going to make your carbon non-reactive. So what we're looking at here is we're looking at 2 examples. One of these examples is correct, and one of these examples is incorrect. I'm going to actually erase all of this, and I'm going to rewrite it where you can kind of see it better. So let's see, hydrogen is going to have 1 bond, right? Oxygen is going to have 2 bonds to fill its valence. Carbon needs 4 bonds to fill its valence. And nitrogen is going to need 3 bonds to fill its valence. So basically, I showed you an illustration. Now I'm just making a little cheat sheet. All right, so looking at my cheat sheet for your, we're first going to look at this example and see if it's correct, see if this is the correct molecule. So I'm going to go ahead and pull out a highlighter so we can follow along on what's going on. So let's look at the carbon first, the central carbon. This carbon is 1, 2, 3, 4 bonds. Look good to me. All righty. Well, let's look at the next carbon, the carbon next to it. 1, 2, 3, 4 bonds. Looks good. All righty. So let's look at the oxygens. 1, 2 bonds. Looks good because it follows the rules. The next oxygen is supposed to have 2 bonds. Let's see. 1, 2. Yep, it has 2 bonds. So let's check out all the hydrogens. This hydrogen is 1 bond. This hydrogen is 1 bond, 1 and 1. So this right here is a correct molecule. Okay, so let's look at the molecule next to it. Molecule next to it, we're going to see if it's written correctly. So let's look at the first carbon, and we know that it's supposed to have 4 bonds. 1, 2, 3, 4 bonds. So we're looking good. Let's look at the next carbon. 1, 2, 3, 4 bonds. That is correct. Let's look at the oxygen. 1, 2 bonds. Yep, it needs 2 bonds. Hydrogens, 1 bond, correct. 1 bond, correct. 1 bond, correct. And 1 bond, correct. But what's going on here? What's going on right here? This hydrogen has 2 bonds. That is not a correctly written molecule. All righty. So you should be able to identify stuff like that. All right, so we've shown you a lot of different things. We've shown you the structural formula. So this is the structural formula that shows the bond. The molecular formula is just how we write it. So when we talk about the molecular formula, as you can see here, there's even more than just that. We have, so the name of the molecule and the molecular formula. Electron distribution diagram. That is where we draw the shells and where the electrons sit in the shells. I had shown you this in your lecture previous. Lewis dot structure. That's when you only show the valence electrons. So as you can see here, it's showing only the electrons, and right here, only the valence electrons. And then the structural formula, that's where you show the line. This is the structural formula where you show the line and so forth. This is the structural formula of water. And last but not least, you'll see this, the space filling model. These are basically models that we have in the lab. You can play with the atoms and put them together in the model. If I pause every once in a while, it's because I put it on mute so I can cough. Okay, so what are we looking at here? We are looking at hydrogen gas. We already talked about that. We already talked about oxygen gas. Right here, water. Water is a molecule, H2O. It has two H's and one oxygen molecule. So it's got two hydrogen molecules and one oxygen molecules. Well, if you recall, those that share are CHNOPs, CHNOPS. So water is following suit. You have your hydrogen is going to share its electrons with the oxygen, and the oxygen is going to share its electrons with the hydrogen. They have a special type of sharing pattern though, okay? It is called polar. We're going to get into that in the next set of slides. Before we do that, let's look at methane. Your methane, as you can see, is going to share electrons. The carbon is going to share electrons with hydrogen, and the hydrogen shares electrons with the carbon, and they share equally. What that means is there's an equal distribution of electrons around that methane molecule. You don't have electrons hanging out unequally on one side versus the other. Okay, so that's called nonpolar. So your water is going to have an unequal distribution of electrons versus your methane has an equal distribution, so it's nonpolar. So those are the definitions we're going to get into next. All right, so this is stuff we've already talked about. All right, so electronegativity. So electronegativity is going to be an atom's attraction to the electrons in a covalent bond, because some atoms have a greater attraction, i.e. pull of electrons, than other atoms. And that is going to lead to a degree of electronegativity. So going into polar versus nonpolar, a nonpolar covalent bond, the atoms, the atoms will share the electrons equally. In polar covalent bonding, you have some atoms that will have a greater pull on the electrons than the other atoms. And so that is an unequal sharing of electrons, and that causes electronegativity. So here is your water right here. So in your water molecule, what you see here, you can see these arrows. These arrows are showing how the electrons will have a greater pull towards the oxygen. So I'm about to show you why. Let's go ahead and pull out my yellow. If you recall, your oxygen has 8 protons. So let's put them in there. 1, 2, 3, 4, 5, 6, 7, 8. 8 protons. And your hydrogen has 1 proton. I'm going to do that one in a darker color. Your hydrogen has 1 proton in its nucleus and 1 proton in its nucleus. Okay, so let's talk about the electrons. So your electrons, your hydrogen has 1 electron, and this one has 1 electron. And if you recall, your oxygen has 8 electrons, but 6 of them are in the valence. Okay, So let's just draw the ones that's going to share, the ones in the valence. So there's going to be a sharing of electrons here, but there's going to be an unequal sharing. So your oxygen is going to have a greater pull on the electrons. And you can see why right here. You can see that your oxygen has 8 positives in the nucleus. So it's got 8 protons. But yet your hydrogens only have 1 proton. So if you can imagine the strongest magnet, how your magnets are going to pull some stronger than others. Well, this has 8 positives against 1 positive. So you can envision how those 8 positives are going to have a greater pull on the hydrogen's electron, which is a negative. And what that does, it draws that electron closer into or towards the oxygen. So it draws that electron closer. All right, friends. So the hydrogen doesn't give away his electron. The oxygen doesn't take it. They're still sharing, but they are unequally sharing. Unequal sharing electrons. So the unequal sharing of electrons, that is called polar. So polar is the unequal sharing of electrons. Your oxygen has a greater pull on the electrons than the hydrogen does. So when that happens, that is going to cause, it is going to cause the oxygen to have a partially negative charge. Didn't mean to do that. I meant to do it with a highlighter. It's going to cause the oxygen to have a partially negative charge. Why? Because the hydrogen's electrons hang out with it more. And then because the hydrogen doesn't get to hang out with his electrons as much, he's going to have a partially positive charge because of the positivity in his nucleus. Partially positive charge because of the positivity in his nucleus. So it is this partially negative charge and partially positive charge that is going to make life possible. And I don't know how to say that any differently. Makes all life possible on Earth. The polarity of water. That is what makes us be able to live here and in general. Think about that. Okay. So this was your ionic bonds. Let's go ahead and skip to your weakest bonds. And then I'll explain why water and its polarity is going to make life possible. So you have levels of bonds that are strongest to weakest, okay? It goes in this order as far as biologists are concerned. I'll be honest with you, chemists are going to have a different order. I know it's kind of silly, but we're most concerned with what is going to be the strongest biologically. So the strongest bonds are going to be your covalent bonds, okay? Then it's going to be your ionic bonds. And then you're going to have weak chemical bonds. And those weak chemical bonds are going to be called hydrogen bonds. So let's go ahead and put them in order. Strongest to weakest. Well, I told you that the strongest bond is going to be the covalent bond. Well, a triple covalent bond is going to be really strong. Triple covalent. And if you can imagine, double covalent, single covalent, ionic, then is the next one is going to be called hydrogen bond. All righty, in order from the strongest to the weakest. So this takes us to the hydrogen bond. The hydrogen bond is going to form when a hydrogen atom, I'm sorry about the doggies, form when a hydrogen atom of one, when the electron of a hydrogen atom is going to covalently bond with the electron of another atom. But, oh, those dogs totally threw off my mojo. I'm going to restate this because the way I stated it was totally wrong. Your hydrogen bond is an attraction between atoms. One of the atoms is going to be hydrogen, the other atom is going to be something else. Okay, so that is the way it should be stated. So for example, let's just go straight into water. Water and ammonia. So as you can see here, you have your hydrogen of one of the waters, right? You got your nitrogen of ammonia. So because of polarity, the hydrogen of your water is going to have a partially positive charge. Well, your ammonia is just like water in the fact that it is also a polar molecule. And the nitrogen has a greater pull of electrons from the hydrogens it's covalently bonding with. Since it has a greater pull, the nitrogen end of the molecule has a partially negative charge. It is that attraction between the partially positive charge of the end of the water molecule and the partially negative charge of the ammonia molecule. That, my friends, right there is the hydrogen bond. And it is weak, meaning it continues to break and reform and break and reform. Okay, so that is why it is the weakest bond. It is because of water, because of the polarity of water, that makes ammonia soluble in water. So if you have polar molecules, any polar molecules, they're going to be soluble in water. All polar molecules soluble in water. And it's all because of this hydrogen bonding. Another type of interactions or close attractions is called van der Waals interactions. So van der Waals interactions is going to be a result of the unequal distribution of electrons on structures, molecules, or atoms. So basically, electrons can accumulate in one part of a molecule. And so your gecko, if you look at your gecko and his toe hairs, these are not really hairs, but you have a huge, great distribution of electrons that literally build up on those areas on the pads of his feet. And because of that, those high amounts of electrons that build up there, that makes it possible for him to stick on to moist walls, because those electrons are attracted to the moisture that is on the walls. That's why you don't see geckos in very, very dry climates climbing walls, but yet you see them in tropical climates climbing walls. It's because of the moisture that accumulates on those walls and structures. Alrighty, so I've said this very many times. A molecule's shape is directly related to its function. This is huge, huge, huge. You are going to hear me say this at every turn, so you might as well learn it now. Molecule shape related to function. Another way to say it, a molecule's so structure related to function, shape and structure related to function. So now all has to do with where the atoms are going to sit in the orbitals. And so you can see here water. Here are your orbitals that we had talked about before. They essentially form a tetrahedral shape, but in some molecules, the tetrahedral shape is full, and in others, it is not. Okay, so Methane would be a perfect example of that perfect tetrahedral shape, where you have your 3D formation of your carbon being in the middle, and then you got your hydrogens in a 3D formation from that carbon. Water is going to be use the basis of the tetrahedral shape, but then it is you're going to have unbonded electron pairs that are going to sit in the other shapes. So it is the shape of these molecules that dictate their functions. So it is so crucial, shape and function. If we want to go to, for example, if you see here, the brain cell is going to have specific receptors, the brain cell receptors. Okay, so those brain cell receptors are going to have a perfect puzzle piece shape to receive natural endorphins. So this is that perfect puzzle piece shape right here. It is going to receive those endorphins. And if you look on the molecule of the endorphins, it has the perfect puzzle piece shape to fit into there. Okay, I know it's a little bit hard to see all the different colors. It's hard for me to choose the correct color here. So morphine is actually a molecule that is given. It's not natural in our bodies, that is. It also has a puzzle piece shape. So as you can see here, even though the rest of the molecule looks like this, it doesn't matter. What matters truly is that the active site of the endorphin receptors in the brain are going to have the shape to receive those molecules of endorphins. So essentially, morphine can take the place of endorphins in order to turn off pain in the brain. It's all about structure and function. So we're going to finish this up with chemical reactions. So your chemical reactions are going to be defined as the making and the breaking of chemical bonds. And so the starting molecules of your chemical reactions are going to be called reactants. And the final molecules are going to be called products. So if I were to draw A plus B, this is the direction of the reaction, is going to make A, B. So over here, these are the reactants. And then over here, these are going to be the products. Now, this reaction can go in the other direction also, where you can end up with AB turning into A plus B. Well, then the direction of it, which one's a reaction and which one is the product, will get flipped. Let's give you an example here. Your reactants and your products. So these are two hydrogen gas molecules, one oxygen gas molecules. They are going to produce two water molecules. You don't get any matter made or you don't get any matter destroyed. Whatever goes into the reaction, the reactant, has to come out of the reaction. So let's count. How many oxygen molecules? 1, 2 oxygen molecules. How many come out? 1, 2. And then how many hydrogen molecules go in? 1, 2, 3, 4. How many come out? 1, 2, 3, 4. So you cannot make or destroy matter. Whatever goes into a reaction comes out of a reaction. And this is just showing the reaction of photosynthesis, where you get 6 carbon dioxide molecules and you get 6 water molecules. So let's see. So 6 CO2 molecules. Okay, you got 1, 2, 3, 4, 5, 6. 6 water molecules, 1, 2, 3, 4, 5, and 6. And so when you get done with that, you end up with 1 glucose molecule and 6 oxygen molecules. So 1, 2, 3, 4, 5, 6. So if you were to add all of these up and count all of the carbon dioxides, count all the CO2, count all the carbons on one side of it, you will have the same amount of carbons coming out. See that? So let's go ahead and there are 6 carbon. So a CO2 molecule has 1 carbon and 2 oxygens. So there are 6 carbons. So carbons equals 6, right? Let's see how many oxygen molecules. 2 oxygen molecules in a CO2, but there are 6 CO2 molecules. Amount of oxygens are 12. And then when you go over here, 2 hydrogens and H2O, but there are 12 hydrogens. So 12 hydrogens. And then there's 1 oxygen molecule in water, but there's 6 of them. So there's plus another 6. So that's 18 total. Let's go to the other side. Hang on. Other side, there are 6 carbons, oxygen molecules. There are 6 here. And then let's go ahead and back up. Let's go to this one first. There are 2 in 1 oxygen molecules, but there are 6 oxygen molecules. 2 times 6 is 12, plus another 6. There are 18 oxygens. And then hydrogens, there are 12 hydrogens. So as you can see, the amount of matter going in, 6, 18, and 12 is the same coming out, 6, 18, and 12. This is just show that chemicals can be reversed. That's what this little sign here shows, that it could go in either direction, where these are the products, I'm sorry, these are the reactants and these are the products, or these would be the reactants and these be the products. That just means that the chemical reaction is reversible. And when the products and the reactants are going at the same rate, that is said for the reaction to be in chemical equilibrium when they go at the same rate. All right, friends, that concludes the rest of our chapter 2. I hope that answers any questions that you might have with your self-study.